Assalamualaikum warahmatullahi wabarakatuh. Saya Ija Pratama dari kelompok 13 akan mempresentasikan makalah tentang distribusi binomial. Yang pertama ada bab 1 pendahuluan. Latar belakang distribusi probabilitas merupakan dasar penting dalam statistik untuk memodelkan berbagai fenomena acak dalam penelitian. Salah satu distribusi diskrit yang paling banyak diterapkan adalah distribusi binomial. Distribusi ini digunakan untuk menghitung peluang keberhasilan dalam sejumlah percobaan independen, di mana setiap percobaan hanya memiliki dua kemungkinan hasil, yaitu sukses atau gagal. Contoh penerapannya sangat luas, mulai dari bidang kesehatan, industri, hingga pendidikan. Penggunaan distribusi binomial menjadi relevan ketika peneliti ingin menganalisis data yang bersifat dikotomi. Misalnya dalam penelitian tentang efektivitas vaksin, responden dapat dikategorikan sebagai kebal atau tidak kebal. Dengan memahami distribusi binomial, peneliti dapat membuat estimasi yang akurat serta pengambilan keputusan yang berbasis data. Masa Makalah ini akan membahas konsep dasar distribusi binomial beserta aplikasi dalam studi kasus nyata. Itu ada rumusan masalah. Yang pertama, bagaimana menerapkan distribusi binomial untuk menghitung peluang keberhasilan dalam percobaan berulang. Terus yang kedua, bagaimana menginterpretasikan mean dan variansi dari distribusi binomial dalam konteks penelitian. Terus yang ketiga, ada tujuan dan manfaat penelitian. Pertama, menjelaskan penerapan distribusi binomial dalam menghitung nilai peluang. Yang kedua, mengimplementasikan nilai mean dan variasi dan distribusi binomial. Manfaat penelitian ini adalah memberikan pemahaman mendalam mengenai distribusi binomial secara aplikasinya dalam analisis statistik. Hasil penelitian dapat dijadikan referensi bagi mahasiswa atau peneliti dalam mengolah data dikotomi serta mendukung pengambilan keputusan berbasis probabilitas. Lalu ada bab kedua, tinjauan pustaka. Distribusi binomial adalah distribusi probabilitas diskrit yang menggambarkan jumlah keberhasilan dalam N percobaan independen dengan peluang keberhasilan P yang tetap setiap percobaannya. Variabel acak X yang mengikuti distribusi binomial dinartikan sebagai X binomial. Pasti boleh dinyatakan sebagai berikut. Distribusi ini memiliki asumsi bahwa setiap percobaan bersifat independen peluang sukses konten. Terus yang ketiga ada metodologi penelitian. Yang pertama, penetapan sampel. Data diperoleh dari survei terhadap 20 mahasiswa yang mengikuti ujian pilihan ganda dengan 10 soal. Setiap soal memiliki 4 pilihan dan hanya satu jawaban benar. Sampel dipilih secara acak sederhana untuk memastikan representasi populasi. Yang kedua, pengumpulan data. Jumlah data yang dikumpulkan adalah 20 observasi. Setiap observasi mempresentasikan jumlah jawaban benar dari 10 soal. Pengambilan data dilakukan dengan simulasi menggunakan software R untuk menghasilkan data acak binomial. Contoh pernyataan survei, berapa jumlah soal yang dijawab benar oleh mahasiswa? Terus yang ketiga, prosedur penelitian. Ada empat, yaitu independensi masalah, pengumpulan data, analisis data, dan interpretasi. Terus yang keempat, bab keempat, pembahasan. Definisi permasalahan penelitian ini menganalisis peluang mahasiswa menjawab soal ujian belajar dengan masalah setiap soal memiliki peluang benar P sama dengan 0,25. Diasumsikan jawaban setiap soal independen. Terus yang kedua, definisi pembacak. Misalkan X adalah pembacak yang menyatakan jumlah jawaban benar dari 10, maka X binomial N sama dengan 10, P sama dengan 0,25. Yang ketiga ada definisi parameter N sama dengan 10, P sama dengan 0,25, Q sama dengan 1, minus P sama dengan 0,75. Terus D dan E adalah menghitung nilai peluang dan menghitung mean dan variansi. Bab 5 kesimpulan. Distribusi binomial berhasil diterapkan untuk menghitung peluang keberhasilan mahasiswa dalam menjawab soal ujian dengan parameter N sama dengan 10 dan P sama dengan 0,25. Diperoleh peluang tepat 5 jawaban benar sebesar 5,84%, menunjukkan bahwa penyampai kombinasi minimal 20% benar memiliki peluang yang rendah. Kemudian distribusi binomial sebesar 2,5 mengindikasikan rata-rata jawaban benar mahasiswa, sementara 1875 mencerminkan konsistensi hasil. Hasil ini dapat menjadi acuan bagi pendidik untuk mengetahui kesulitan soal dan meningkatkan kualitas pembelajaran. Sekian dari saya, mohon maaf apabila ada kesalahan. Assalamualaikum warahmatullahi wabarakatuh.
If a 60% free throw shooter takes 10 shots, what is the probability that it makes exactly 7 of them? To answer questions like that, we can use this formula for the binomial distribution. And this doesn't just apply to free throws. It applies whenever there's a repeating process where you could put the outcomes into two categories. That's where the bi in binomial comes from. And that kind of situation is pretty common considering it encompasses all yes or no questions. The formula looks a bit scary, but by the end of this video, we'll make sense of it, and hopefully it's pretty along the way. Okay, we're gonna start with one blob. It's programmed to make it 60% of the time, so what's the probability that it would make 1 out of 1? This question feels a little bit silly. We don't need any fancy formulas to know that the answer is 60%, but it's a starting point to build on. Another silly starting question is, what's the probability it makes 0 of 1? It's the other 40% of the time. 60% is the same as 3 out of 5, so we can visualize the probabilities by looking at 5 blobs and having 3 of them make it and 2 of them miss. Okay, now what if the blobs take 2 shots each? It'll be helpful to have more blobs to look at here, so let's make this into a square of blobs and have the new blobs also take their first shot, again with 3 out of 5 of them making it. And then they can all take a second shot, which means we now have to ask about making 0, 1, or 2 of 2 shots. You might notice this isn't exactly random, but for the moment we're just focusing on making a clean diagram. 4 of the 25 blobs were unlucky enough to miss both the first and the second shot. From this, we can say that a 60% free throw shooter has a 16% probability of missing both shots. And this is the same number we would have gotten by multiplying the probabilities of the individual shot outcomes. The probability of missing the first shot is 40%, then 40% of those 40% also miss the second shot, and 40% of 40% comes out to 16%. Next, for the blobs that made 1 shot, we have 2 groups. One group of 6 made the first and missed the second shot, and 6 out of 25 is 24%. Again, we can multiply the individual probabilities to check that they come out the same, and indeed, 60% for the make times 40% for the miss comes out to 24%. The second group is pretty much the same, except the make and the miss come in the opposite order. And adding these together, we get a 48% probability for making 1 of 2 shots. And for the ones that made both shots, there's again just one group, and we can fill in the numbers in the same way. And all these probabilities add up to 100%, which is a great sign. We're gonna add a third shot in a moment here, but it might already be possible to guess at the pattern. So try pausing and see if you can predict what it's gonna look like after 3 shots. Okay, for the third shot, it'll be useful to have even more blobs to look at, so let's make this a 3D grid and have the new blobs take their first 2 shots. With 3 shots, the top 3 layers made it and the bottom 2 layers missed. It's a little bit difficult to see what's going on inside this cube, so let's pull it apart into sections and organize it by outcome. Okay, so again, there's only one way to miss all of the shots. 8 of the 125 blobs ended up in this category, which gives us a probability of 6.4% for that outcome. And again, we could get this same number by multiplying the probabilities of the individual misses. Next, for 1 make out of 3 shots, there are 3 ways to get it. The first way in this list is miss, miss, then make. 12 of the 125 blobs had this outcome, which gives us a 9.6% probability. Multiplying the individual probabilities looks like this. The thing to notice here is that all 3 of these groups have the same number of blobs in them. The probability is the same for each of them. We don't care about the order of makes and misses, we just care about how many there are. And order also doesn't matter for multiplication, so each of these comes out to the same 9.6%. which means we don't have to go through all the different ways of making one of 3. We can just calculate the probability for one of them, then multiply that result by 3 to get the overall probability of making 1 out of 3 shots. And this idea will come in handy for looking at 2 out of 3. Just like before, there are 3 groups, and they each have the same probability, which is 14.4% each, for an overall probability of 43.2% to make 2 out of 3. And for 3 out of 3, there's just one way with a probability of 21.6%. So we have this pattern of counting the number of specific ways to make a certain number of shots, and then multiplying that by the probability for each of those specific ways, which again are always the same. And that's exactly what this formula does. This bit here stands for the number of ways to get k makes out of n total shots. It's called the binomial coefficient. In this example we just went through, the binomial coefficient is 1, 3, 3, or 1, depending how many makes we're asking about. We don't yet have a great way of finding it for other numbers of attempts and makes, so most of the rest of this video is going to focus on that. And the second part is multiplying the probabilities of the individual shots. This little p is the probability of a success, so 60% in this case, and 1 minus the little p is the probability of a failure, so 40%. And if we write these calculations so far using exponents, you can start to see how they have the same shape as the formula. So this formula has a lot of pieces and a lot of letters, so depending how much practice you've had with algebra recently, it might feel a bit overwhelming. If so, I can guarantee you're not alone. And it might be a good exercise to pause, take out a piece of paper, and plug the numbers into the formula for each case yourself. Now, all the math nerds out there are going to yell at me, with good reason, if I don't mention that this formula only makes sense if the shots are independent of each other.